Hello, my name is Ilya Mandel. I'm a professor of theoretical astrophysics here at the Monash School of Physics and Astronomy. And I'm going to try to use this Lycra universe to explain how gravity works. Now, you might be wondering what this thing is doing here. I'll explain in just a second. But first, let me remind you how gravity works according to ideas that Newton developed 400 years ago. So in Newton's notion of gravity, there are two massive objects. They exert a force on each other. They attract each other. That force is proportional to their masses and inversely proportional to the square of the distance between them. But there are some problems with this. One of the problems is that gravity in Newton's theory propagates instantaneously, whereas Einstein realized early in the 20th century that that doesn't make any sense because information cannot travel faster than the speed of light. There are a few other problems with this idea, and after pondering this for more than a decade, Einstein came up with something that he called the general theory of relativity, which is really Einstein's theory of gravity. And it says something like the following. It says that gravity is actually a curvature of space and time. Now, I don't quite know how to show curvature in 4 dimensions, so I'm going to use this Lycra universe to show it in 2 dimensions. Now, the first idea is that if we have a flat space-time, look, here's a flat surface, then any object is just going to move along with a constant speed in the same direction it was initially moving in. So here's my little marble. I roll it along, and you can see it's following a fairly straight path along this flat surface. But now suppose there is some big, massive object. What this massive object does is its gravity curves the space and time around it. You see it here as a funnel in this Lycra universe. And now, if I take my little object and I again try to move it on a straight line by giving it some initial speed, you will see that what it actually does is it curves around. It zooms around this big, massive object. Right? Let's try it one more time. You can think of this as a kind of planet that's orbiting around the sun, for example, at the center of the solar system. Now, that's all well and good. And OK, in general, if there was no friction, this orbit would continue forever. But you can imagine a different situation where now my second object is also fairly heavy. Now here, of course, in this simple illustration, it's just going to have a little bit more friction. But in reality, what's going to happen is a phenomenon that Einstein predicted called gravitational waves. These are ripples in the fabric of space-time that you can see here. You can see that there's some shaking of my Lycra universe, the shaking of space and time. And of course, you can see that this object spirals in much faster now than the little pebble did because it's losing extra energy that propagates out as the ripples in space and time. And these ripples, in fact, were predicted by Einstein in 1916, but were not observed until exactly 100 years later when the Laser Interferometer Gravitational Wave Observatory, a big international collaboration that Monash is a major player in, first detected gravitational waves. And this is one of the very exciting topics of research here in the School of Physics and Astronomy at Monash, where we have a big group that plays a major part in the LIGO collaboration, trying to detect gravitational waves from the mergers of 2 black holes or 2 neutron stars, very dense, very compact objects, and trying to understand what they mean as far as the evolution of massive stars and the tests of general relativity on the most extreme scales imaginable. Thank you.